Welcome to Process Control Design and Practice. My name is Tom Meadowcroft. In this video, we will learn about modular batch design. In the last video, we wrote a batch recipe and learned to express it as sequential logic using a vocabulary of actions, transitions, and decisions, and then draw it as a structured function chart. It resembled a chemist's description of how a batch would run, largely because the actions we were restricted to were pretty big picture. Actions like charge A and reactor temperature control. Clearly, there's a lot of detail hidden in the words charge A. Charging A requires pumps to run, sensors to measure flow or mass, and valves to control it. If we wrote out the detail describing that same batch, where every pump turning on and off, every valve opening or closing, and every parameter change required a line of computer code or another action block in a sequential function chart, the code would be a dozen pages long. Many blocks of the code would repeat for every time we did a temperature change or a similar charge. And if we had 10 reactors in our plant where we ran this recipe, there would be a dozen pages of code for each, mostly similar but with different device names. Now imagine a company that has 4 plant sites with 10 reactors in each, and each reactor is capable of making 30 products with similar but differing recipes. You end up with an unmanageable mountain of software filled with small errors, difficult to change, and a source of frustration and inefficiency. And this, in fact, is what happened in the early days of batch automation. To manage this complexity, engineers began to use modular levels of abstraction and eventually wrote a standard, the S88 standard, that everyone follows today, more or less. It is a standard of the Instrument Society of America, ISA, and the American National Standards Institute, ANSI, but it is used worldwide. It allows us to divide batch sequential logic into bite-sized pieces that are much easier to deal with. There are 7 layers of abstraction to the S88 model, ranging from enterprise, plant, area, process, unit, and equipment, and down to control device. A module at each level is made up of one or more modules of the next lowest level. So an enterprise is made up of one or more plants, and a process module is made up of one or more unit modules, and so on. The key to the standard is that at each level, you only need to describe enough detail to manage that level. So at the process module level, a reactor unit simply receives raw materials and produces product to a specification. The process level doesn't describe how. Think of it like a process flow diagram. The reactor unit module has a recipe, like the one we wrote last time, that describes the steps to carry out that reaction, but it doesn't need to know how charging and how temperature control are achieved on a particular unit. We leave that to the equipment modules, and so on. We're going to focus on the lowest 3 levels of S88. A unit module holds one batch and is capable of running one or more unit recipes which act on the batch. So a batch reactor is a unit, or a batch distillation column, or a mixing tank. A unit module is made up of one or more equipment modules. An equipment module controls one function of the unit. So the reactor might have a temperature control unit, which includes all the equipment to control temperature, like heat exchangers and the associated sensors, valves, pumps, and controllers. Just as unit recipes document the sequences that the unit runs, each equipment module has one or more phases. So the batch charge equipment module for our batch reactor, capable of charging A, B, or the condensate receiver, would have 3 phases: charge A, charge B, and charge receiver. which document the necessary sequential logic necessary to do each. The elements of the equipment module are called control modules, which are all the elements of the equipment state that can be manipulated or produce signals, so sensors, valves, pumps, and control loops. A feedback control loop is a control module made up of a sensor, a valve, and a controller, which are also control modules, which is why the extra arrow there points back at itself. So a control module can be made up of other control modules. Control modules don't execute sequences. They have a changeable state or parameter, like on-off, open-closed, a measured temperature or pressure value, a set point, or a controller output. Here are some examples of control modules. A solenoid valve receives an open or close command and is either open, closed, or in transition. A resistance temperature detector, or RTD, outputs a temperature measurement. We can set alarm levels for it and receive alarm statuses. A variable speed pump receives on-off and speed commands and reports being either running or stopped and the actual speed. A level control loop is a PID controller, a level measurement, and a control valve. The controller can be told to be in automatic, attempting to control the level to a set point, or manual, allowing direct control of the valve. It reports back the measured level, the control valve position, and any alarms that we've configured. Phases are the sequential logic for an equipment module. Phases are the actions that make up a unit recipe. When the unit recipe needs to charge 3,000 kilograms of A, it uses the command charge A 3,000 kilograms. Charge A is the name of the phase in the batch charge equipment module, and 3,000 kilograms is the target parameter for this one use of charge A. We'll use it later with other charge values. Charge A is a sequence that we're going to document using a sequential function chart, but where the unit recipe sequence used phases as action commands, phases will change the state of control modules, issuing commands like open valve, start pump, switch the controller to automatic. We're going to spend all of the next video writing phases. The reason breaking up the batch into modules is worthwhile is that each of the modules is relatively simple. Most sequential function charts for a recipe or a phase are 1 to 2 pages, and more often 1 than 2. And they can be reused. A batch recipe for making polystyrene beads may need to charge styrene 6 different times, with a different mass target for each charge. In the unit recipe, that appears as charge styrene 400 kilograms, then charge styrene 600 kilograms, and so on. There's only one charge styrene phase. It knows how to charge however much styrene the batch needs. You reuse the same phase with a different target over and over again. If something changes in the way we charge styrene for a unit, only the one simple phase needs to be changed. Finally, while the phases have to be very specific to their particular control modules, the unit recipe doesn't depend on a particular piece of equipment. The same unit recipe can be used in different reactors or different plants. As long as the unit has the capabilities needed, the phases the recipe requires, the unit recipe is portable. Just scale the recipe mass and volume parameters for the unit volume. This video has introduced the idea of modular batch design and the S88 standard. That described a hierarchy of abstraction, and we focused on the lowest 3 levels, the unit, equipment, and control modules. Units are made up of equipment modules. Unit recipes associated with unit modules run phases associated with equipment modules. The equipment module phases read and manipulate the states of the control modules that make up the equipment module. The control modules are the devices, pumps, valves, sensors, controllers, and so on. S88 allows us to complete complex batch operations by combining relatively simple pieces of sequential logic. In the next video, we'll learn about writing phases. Look for a full text, exercises, and more videos at chemicalengineeringpractice.org. I'm Tom Meadowcroft. I hope to see you again soon.